Okay, well, let's get started. Just wanted to say a few words about myself if you don't know, and why am I speaking about this topic. I've been involved in the open source and especially open source database community for a long time. And so obviously as vector search is gaining a lot of interest, so it picked up my interest too. So here am I talking to you about it. Now, why vector search? Why is this topic so relevant those days? Is because you can really see it everywhere. Even if you don't know it in a lot of the products, what you are using those days are using vector search underneath it those days. Now let's talk briefly about the vector search support in databases. And I think here we have a very interesting situation. You can see what in the last few years, vector search came really out of nowhere. If you look at before 2019, there was kind of really no support of that in the databases. And now almost all the databases have support to that by 2003, some getting that in 2004. The interesting exception in this case is their MySQL, which is kind of with the Oracle leadership kind of has taken a route what they don't have a vector search in open source MySQL version, and that's only restricted to their cloud heatwave edition. And you can really see with vector search being so hot, many databases are promoting that. If you think about Elasticsearch, they have been really changed it and talk about themselves as a world most downloaded vector databases. You can see the enterprise DB also has been focusing a lot those days at AI, also doing some sort of rebranding as Postgres AI, right, versus rather than general Postgres. Then vector search is hot because AI is hot, and vector search is how AI is presented itself in a databases. But before we get to maybe more details, let's talk about the vectors. And I know some folks which are not very familiar with the fields, they kind of wonder, okay, we understand the AI is big, machine learning is big, right? But why are we talking about vectors in the databases? And the reason is this. If you look at AI and machine learning technologies, right? They don't really work with words, images, or videos, sounds. This is a complicated math algorithms, and underneath them there is a lot of linear algebra and other math, and the matrices and vectors are really the foundation how that math works. And all those real world objects are really presented in sort of mathematical representation as vectors. Now, what are vectors and what operations do we have with them? I think one of the easiest way to illustrate what vectors are is many of us know what the light, so like or colors, right? For example, in the computer screen, we can see what the light can be represented with RGB values for red, green, and blue. And those three components, they correspond to a vector, which gives us a given color, right? For example, color orange, right? And what is interesting in this case is using that vector notation, we can talk about how different or how much the same the colors are. And also we can talk about the different similarities in this case here as well, right? For example, for some applications, it is a luminance which is more important, right? And that tells about the length of a vector, right? So is it bright color or not? For other ones, it's maybe what the colors, right? Like a very dull orange and very bright orange would be considered more of the same. Therefore, other applications, a very bright green and bright yellow is the same, right? So what that tells us in this case, when we speak about a vector space, we have a vector similarity, and we are talking about certain ways to compute the distance between those vectors, which there are a number of formulas which you can use. If you look at the OpenAI, which are sort of a standard setter for a lot of AI applications. They recommend you just can use cosine similarity because of the embeddings OpenAI uses or produce normalized to a length, and that means they're pretty much the same. Now, let's talk about how data can be mapped to those vectors. And again, vectors have been in our space long before the ChatGPT came to the pictures. The two very common ways what we deal with the vectors in a data space are two structures. One of them are called sparse vectors. And these have been used for a while in a full text search applications. That is where you would have, for example, their vector space, right, where we would have every word would have a number associated with that, and when we look at the text, we can map for value, right, or frequency for any word in that document, right? Obviously, especially for small documents, most of the spaces will be zero, right, or empty because there is no word of that document. And that is a very good presentation that's has been used a lot of full text search applications. The other approach is a dense vector. And a dense vector, it corresponds to the case where in every dimension, every value in a vector, there is actually not an empty value, right? So it's kind of contains data kind of more compressed. And when we are talking about embeddings, which is a foundation of a lot of AI applications, these are dense vectors. So let's think about this simple use case scenario. Let's imagine what you want to compare the similarity of the words cat and dog or cat and car, right? And there is multiple ways to do it. If you go and compute sort of like a lexicographical word distance, then a cat and a car would be very similar because they are only off by one digit. It's as well could be a typo. But if you think about the meaning, of course, cat and dog would be very much more similar, right, than a cat and a car. So how do we get that meaning from words, right, for example? Well, that is where embedding helps us. There are a lot of those LLM models which can produce our embeddings, kind of vectors which are with a lot of sort of like a different meanings, right, which corresponds to different objects, words, text, images, right, sounds, it depends. Now, you may wonder, okay, we get that vector, but what is going to be inside? And here is a very interesting example from Wikipedia. They run through a model, different words, and build that into sort of relatively small, relatively short dimension embedding, right? And what we can see in this case is, well, you kind of maybe guess as a human, right, about, well, this column could possibly mean this or that, right? But you can only guess and imagine. There is actually no well-defined meaning for that, differently from the example with color we had, right? Because if you speak about the color space, okay, we have a three components of that vector, RGB, right? Each of them have a meaning, right? And there are many vectors like that where every value has a meaning, but that's not specifically in embedding. What embeddings are is more like magic, right? We give an object, our AA model gives us its own magic and generates as embeddings. We know some properties about those embeddings, embeddings for, or vectors for, let's say, cat and a dog would be similar, more similar than a cat and a car, right? But we cannot really talk about meanings of a specific values. And so what is also important about those embeddings is there is no right or wrong embeddings for particular object. They depend on the model and even configuration, right? That's why you have to be very careful if you store embedding in your databases, not to sort of invalidate them by changing to a different model or configuration. Now, if you think about vectors, you may tell, well, you know what? Databases had support for a very long time to be able to store arrays of data. So what is the problem, right? Why cannot we just stuff data in arrays, right, or blobs, which a lot of the databases support? Well, the problem comes not really with storing the stuff, but in terms of being able to operate on that stuff, right, and especially being able to look it up. If you really use a database and store your embedding as a blob, right, and then you would need to, let's say, find embedding similar to a vector you have at place, well, you just have to do a full table scan and do a lot of very, very complicated computation, which is not going to work. And optimization data structures like a B-trees, or even kind of hash indexes, bitmaps, none of those conventional data structures, they really work well for optimizing access to embedding, right? With that, if you look at their methods which are used in the vector search databases, they are different. They come with specialized indexes, right? Like HNSW is, I would say, most common algorithms used those days. What is also very interesting in this case, right, and which is kind of maybe kind of counterintuitive for our like relational databases and such, is what those indexes are kind of approximate data structures, right? When we talk about the embedding lookups and comparison, we are talk about something like probabilistically, right? What we are with a high probability is going to find the most close vector or things like that, which actually are quite usable for this ecosystem because the mapping of the objects to a vector is kind of not exactly defined anyway, right? It's not like 2 plus 2 equals 4 and any other answer would be invalid, right? If AI, it's kind of much more fuzzy, right? It just kind of have to make sense. Well, how you can check this in practice? Well, there is a little link for you with vector search used by Demo, built by Manticore core guys, right? And here you can see their a good example on the GitHub issues. GitHub itself doesn't have a full search for vector yet. It just have a conventional full text search, and that may be kind of limited, right? We can see in this example, if I'm looking for memory leak, well, you know what? Not every developer may talk about those things as memory leak, right? In this case, we can see some other things like crash because of a lot of memory usage, huge RAM usage, and so on and so forth, right? It doesn't have the memory leak words, but a vector search by computing embedding on the search phrase and all the documents exist in the database is able to figure out this is kind of somewhat similar, right? And they have to be relevant. So if you think about where the vector search and other areas can be useful, there are few of them in this case. And let me go on a very high level about some of them. One of the tasks which vector search database and vector extension can help us is clustering. And the clustering tells us, well, you know what, we want to group the objects somehow automatically together, right? For example, in our examples of cats and dogs, right, we may find like a cluster of animals together, right? And that is very useful, right? For example, if you want to find the similar products, right, or something like that in the space, right, or any kind of other recommendation. Another task where embedding can be very commonly used is their classification. And what with classification happens is we are able to assign certain class, again, like an example I said before, cat and dog, instead of just saying, well, cat and dog kind of, somewhere similar, we don't know what is similar between them, we can, as a human, define, what those objects they are actually animals, right? And as we do that by tuning the system for many other objects, hopefully it can then help us to classify and say, oh, this is also animal, right? As a frog, right? And so the car is not an animal. Again, that can be used in a lot of use cases, from products categorization to spam filter and medical diagnosis and so on and so forth. And then if you look at a very low level thing, which underpins a lot of work, right? It could be nearest search, right? Or approximately nearest search. There we are extending, that is the core functionality which exists in vast majority of databases, which says, well, I have a vector X, please look me up. I say, what are the closest vectors which exist to that in a database? And that is a very interesting, because that often can sort of respect or replace a lot of that kind of manual work which you have been doing in a full text search databases, like morphology, synonyms, stop words, and typos and so on and so forth, right? I mean, if you have a good LLM models, it just can cover all of that after magically, and you still would find what the text, if misspelled and using different synonyms, right, would be still mapped as I showed you in the example. Okay, now unless you've been living under the rock, you know what, if it comes to open source databases, their PostgreSQL is by far getting a lot of momentum out there. And so if you talk about vector search in database, we should talk about vector search in Postgres as well. So if you look at vector search in Postgres, it comes in multiple layers. On one extent, we have a PG vector, which is actually like a core functionality, which just provides us with that mechanics, right? The index and so on and so forth, right? Then there is a PG vectorize, which provides the functions for interfacing with different models like OpenAI, Llama, and so on and so forth, right? Including functions for embedding generations. And then there is also a platform called PostgreSQL ML, which is a whole platform to really build AI-powered app with Postgres. But let us go to basics maybe to imagine how it is. So if you are looking to store vector data in Postgres, we can define a table, the type vector. In this case, again, for simplicity, we show very small dimensions, right? We create the index on which defines the vector, as well as what exactly similarity which we'll use, right? We're using cosine similarity here as decided. And then we can insert a couple of data out there. Let's imagine these are embeddings which have been generated with some sort of LLM model, right? And then we can, let's say, got another data, and then we going to look and see, hey, how does it compares to vectors in this database? And we can see whatever that was looks a lot more similar to yellow bag compared to white bag, right? So that is pretty much how it works. Now, if we talk again about the full text search applications, I have highlighted what we can use our vector search for full text search application as well. But what is exactly the problems here? Well, it's not complete all the benefits. It has a high computation costs, more memory, more storage, right, for all those indexes. A result not as explainable, right? Like if you have a lot of search results in something like a Google or maybe your product search engine, you often can tinker with them and say, well, you know what, this is ranking high, but it should not be, right? Or something else is not being found. You can debug that, which is much harder with embedding, because remember, embeddings are magic, right? And also there are not quite exact match in which you want to do. And that is why you would often see the hybrid search approaches used, which on one side, they do give better results, better relevance, right? What we see here in this case, there is in the full text search or information retrieval field, there is their own kind of accuracy benchmarks, which are the different algorithms are compared on. And we can see in this case is what the hybrid algorithm actually in most cases performs better than either plain vector search algorithms or plain kind of classical full text search matching with BM25. But what is also fantastic is what that allows us to use the different modes depends on what requirements are, right? For example, if you want to use exact phrase match, then we can utilize just a full text search, and if otherwise it's something different. Here is another example, right? What you can do. And by the way, this one is also simple application, which is open source, which you can, same as a GitHub one, which you can download and play with it, right? And then we can see in this case how we run a bunch of different products through the LLM system, and we can see what you can actually look for, formal shoes or running shoes, and get pretty good results, even though none of these do not actually come in the shoes description. It is just, in this case, the image was processing through Microsoft's tiny clip model, and it gives us pretty cool examples. Well, then, of course, I cannot not touch on a generative AI, right, which is obviously all going places where we go besides search, classification, and so on and so forth, but those applications. What is a really big deal, and there you would see the vector search used together with solutions like a ChatGPT, is a concept called retrieval augmented generation, right? Which is a concept where you can sort of combine ChatGPT smart and generation capabilities with some your enterprise data, right? For example, you have information about your product, and you can build a bot which is informed about your product, but also have a ChatGPT smart, right? And is there a lot of development going on those days, because it really helped to optimize a lot of workflows. Now let's talk about what next and what's going on. Well, one thing I think is interesting in what we have seen is there a lot of specialized databases. They started already through integrating the embedding generation in them, but their traditional databases, which started to kind of add support for vector search, initially did not provide any embedding generation, just saying, hey, we just store that. Now we are increasingly getting that integrated more and more. And this is, of course, quite expected, because the idea for the databases to become the better tools for developers building the new type of those AI enabled apps, right? And we still figure it out, right? That's obviously going to be more than just a storage, right? And additionally, there is a lot of work going on beyond the databases in creating tools to just be able to generate application with code. If you look at specifically at the vector search databases, there is a lot of other things that we may be looking at, right? We are seeing increasingly the ideas how we can go from just storing and processing information to being able to provide some AI-powered insights. And this goes kind of beyond the algorithms of itself. You guys may have seen there are solutions for generate SQL, or even saying, hey, you can connect your data sources and then ask questions, and the AI will automatically find out where the data resides, how to write the query, and retrieve the data you are looking for. Okay, well, to finish it up, I think it's very interesting to see how a vector search is transforming data retrieval. And for me, it's interesting to see that as it's kind of deja vu, right? When we previously had, for example, JSON data type and a challenge, right, which also was coming into the databases. And as usually what happens in this case, we have two trends happening at the same time. On one extent, we have the special purpose databases, right, which are built specifically for this problem use case, but then also for a lot of simple use cases and the applications. We see the databases like Postgres getting a lot of functionality as well, where it remains to be like good enough for those applications. So that is all I wanted to say.